I'm Dave Fancher from Carmel, Indiana. Today we are going to talk about Elm. I dabble in a few things myself. One of the things that really attracted me to the Elm language is that it is a derivative of ML, just like F#. So for me, having some background in F#, coming into Elm was a very easy transition. The type system, the Handley-Miller type system, is incredibly similar to the way that F# works. There's pipelining, and we have discriminated unions, we have record types, so all of those things translated very well. Now, why would I be looking at Elm to begin with? Well, for me, coming into Elm was one of those things like, okay, most of my work is on the back end. But every once in a while, I need to do something on the front end, and I really didn't want to work in JavaScript. I'm sure a lot of you can relate to that. And I had started going down being a Microsoft guy, looking at TypeScript. And don't get me wrong, I like TypeScript. I think TypeScript has a lot of great things in it, especially some of the later versions. But what I started realizing and started thinking about TypeScript was, if this is really just a superset of JavaScript, why don't I just learn to write JavaScript the right way? And do the things that the compiler is doing. It's really not that hard to make the mental conversion from using class in TypeScript to writing a function as a closure, right? So I don't really need that extra level of complexity. Yeah, there's a case to be made that it's a little bit more readable, but if I'm going to write that code, I might as well just write it the JavaScript way and keep all of the TypeScript stuff out of it. But then I'm still in JavaScript. And I don't get a lot of the assurances that other languages that I'm used to, like F#, would give me. But Elm, being a derivative of ML, makes it very easy to get some of that safety that I've taken for granted in other languages. So one of the things, being an ML language, it's a purely functional language, and it is intended primarily for front-end development. And we'll see at the sample application toward the end of this talk how what we call the Elm architecture really facilitates front-end development for us. I already mentioned that it was derived from ML. It's statically typed. I mean, it's a Handley-Miller type system, statically typed, great type inference. I do kind of like the way that it requires us to annotate our functions with the various types involved, but it does do a lot of type inference as well, so it's beautiful on that front. And as a functional language, it's expression-based. So everything returns everything has an input, everything has an output, and then because it's browser-based, everything compiles to JavaScript. But Elm is not, like TypeScript, a superset of JavaScript. It is its own independent, unique language. All right, let me skip this slide, so we talked about it. Sure. One of the things that you'll find as you start digging into Elm, aside from it being a purely functional language, as I mentioned, meaning immutability, limited side effects. Actually, there are no side effects because everything works through essentially a message-based system. And my favorite part, as you can tell from my license plate, is there are no nulls. So I didn't even have to type from that. Yeah, I drive around Carmel, Indiana with that license plate. Yeah, every once in a while I see a tweet, hey, I'm behind Dave Fancher. Like, hey, cool. And I don't mention it on this slide much, but just the friendly compiler errors. I'm sure as we're typing some of the sample code in a little bit later, we will run across a few of those because undoubtedly, as I'm in the REPL, I'll forget a backslash or something, and it'll tell me in a very friendly, consumable way not only that there was an error, but what the error was, and most of the time, what to do to fix that error. Because the nature of the language is such that the compiler can have more insight into what the code you're writing is trying to do, it can give you more helpful error messages. And I think that's something that we often lack in software development is error messages that actually tell us something useful. And finally, it's cross-platform. Most of my work is in Windows and .NET, but today I'm running on a Mac. I don't have my VM running. We will see that it works really well. I've had to install a few components. I don't have those listed in this talk. The instructions on the Elm language website are very thorough, and it's quite easy to get set up with. If you want to install it, it's available on Windows, on Mac, other platforms. They have installers. You can get it from Node. And then you can always build from source because it's an open source project. Editors, choose your editor, use what you want. I choose VS Code. There's an extension for Elm that plugs right into VS Code, gives you access to the REPL, and a few other utilities that are incredibly useful when developing an Elm application. And I can bring up the extension list in code when we get to that. So Elm is really a platform of its own. Yes, there's this language called Elm, and we write this Elm code, but we have a REPL. And all of these are console applications that we can use to either test our code, or build our code, or package our code for distribution, or get third-party packages that we want to consume in our project. What's really nice about the REPL is, and working with VS Code, is I don't have to jump back and forth to a terminal window because it has the terminal built right into VS Code, and so I can go back and forth between my code and the REPL and do that testing of the code that I'm trying to write at the time, right in line, no context switching, and it's quite useful. And then you can also send code as you've written in the editor window. You can have it sent and directed down to the REPL window and have it evaluated on the fly. It's really, really nice. So before we dive into a sample application, let's take a little look at the language itself. I'm going to kill PowerPoint here because we should be done with that. And let's see, I have to zoom this in a little bit more. I'm just going to open up a terminal window here in VS Code. How's that look in the back? Good? Okay. So just like languages that we're used to, let's just do a little tour of some of the features of the language. As with most languages, any language, we have our, helps to be in Elm, right? Notice I'm in Visual Studio Code, I've got my terminal window open, and I'm at a bash prompt. And now I'm in my Elm REPL. I've got the interactive console window here, so I can look at things like true and false. And we can see these are evaluating. Notice we have our types, though. If this was JavaScript, which behind the scenes ultimately it is, we have some limited types, but they're all variants and whatnot. This is going to be strongly typed in the Elm sandbox. We have strings, we have characters. Now, let's look at one of those messages. Oh, look at this error message. I forgot my closing apostrophe for my character. Ran into something unexpected when parsing your code. I'm looking for one of the following things. It starts this list. It only has one suggestion here, a closing quote. Like, that's pretty helpful, right? And as you get into other things, like discriminated unions, you'll see, oh, I'm expecting a pipe, or some white space, or any of the other things that may be syntactically wrong because it knows just what you're trying to do and it knows the context of your code. But one of the places where it really differs from JavaScript is 42 is a number. That's a type we would recognize from JavaScript, but what about 42.0? That's a float. So we have that differentiation in Elm where we can work with both integral data and floating point data, and it makes a differentiation. We can't just pass them around arbitrarily because we're working in a type-safe environment. We do have lists. We don't really have the notion of an array, but we do have lists. They look like JavaScript arrays, but it's a list of number here. I can do lists of strings, but I can also do things like tack on 5. Let's say 5 with what we call the cons operator. I'm going to tack that onto the front of the list. Right? So we have that flexibility. And all of these lists, like lists here, there's a module behind the scenes that we can work with to do things like deciding whether a list is empty. I'm going to define a name here. It's going to call it my list. And it's going to get 1, 2, 3, 4, 5. So we can do things like list.isEmpty my list. Of course, I've got a number of elements in there. I can do things like list.reverse with my list. And so it's going to reverse the order of those items. And I can do list.sort. Notice these are all functional. This is not something, I don't have these properties or methods on the list. I'm working with them as individual standalone module functions. So if I sort, I get 1, 2, 3, 4, 5. But none of these, because we're working in an immutable environment, none of these are actually changing the underlying list. So if I type my list here, then sure enough, I see the original list. Now we get into some of the more interesting types. One of them that got me really excited when I started learning Elm were record types. So I can group data with names. I don't think of them as a lightweight class. It's a good way to think of them. It's a series of names and values, not a dictionary. It is actually like properties. So I'm just going to create a person here. Let's say first name, Dave, last name, Fancher. And now I've created this type that has a first name property and a last name property. I'm going to create another one of these. But this one I'm going to make after my daughter. I don't need to start a new one. Say I have a more complex thing. Say I'm working with colors or anything else, and I have one value that needs to change. So I'm going to change the first name to my daughter's name. So I start like I did the previous line. I have the curly brace. But instead of saying a property right here, I'm just going to take the original record type. In this case, it's me. And I'm going to specify a new value for first name. So I have the exact same structure with a value replaced. And my original record type is unchanged. And then we can work with those just like we would with a JavaScript object, for instance. So if I could say me.firstname or me.lastname, we can pull those values out. But we're in a functional language. Accessing things like properties isn't necessarily the way you'd want to do this. One of the things that Elm gives us is there's a notation that allows us to treat those individual property names as functions. I think this one's really cool. So I've got these two people records, for lack of a better description, and I want to just pull the first names out of that list. Now I could say me.firstname and daughter.firstname, or I can do this more functionally. So I'm just going to start off with list.map. Is people familiar with maps? Functional background? Okay, so I'm going to just use the built-in map function to go and pull out the first name from each of these person records. I don't need to do anything beyond start with a dot and say first name, and now I want to give it the collection, the list that I'm working with, and that's me and daughter. And that's executed that function against every item in that list and just extracted that name. So if you're trying to do list boxes or whatnot, and you have a key value pair, for instance, and you want to extract a particular piece of data from that record to build up a list box, as you would probably do in Elm, this is a very convenient way to go about doing that rather than defining a lambda expression or something that does something that the language already knows how to do. One of the things that's interesting on record types before we move on is that the property names do need to begin with a lowercase. So if I was to come back up here and let's say I'm just going to change the property name to begin with an L, end of input and white space. So it doesn't recognize that structure there because I didn't start with a lowercase l. This is one of those instances where the error message isn't as particularly helpful as where the rest of the language kind of shines, but that is one of the little quirks of this language. Okay. So I didn't ask before. I asked how many people had some experience with Elm, but I didn't ask how many people have experience with a language like F#. Anybody in here have F#? A few? Okay, so it looks like we've got a crowd pretty well versed in discriminated unions, and guess what? We have those in Elm. So one of the examples I like to use to show how the discriminated unions in Elm work is a suit of cards, right? You have a very finite set of cards in a standard deck. We have 4 suits, 52 cards, right? We have certain values associated with each card. Well, we can easily define discriminated unions to represent a standard deck of cards. One of the quirks of the REPL is going to show up here. So I'm going to start defining this. Type suit. And to do multiple lines, we need backslash. And this is where I will undoubtedly miss a backslash as we're typing this. Most of the time I'm working straight in the editor. So we have heart. This is one of the places that does deviate from what I'm used to in F# as I'm working with discriminated unions. With F#, we have the first union case has the pipe, preceding pipe is optional, and I almost always put it in just to keep it consistent. And it does not work like that in Elm. We have to remove that first pipe. So that was a little quirky for me. I would prefer to have that there. It just lines up much nicer when you're looking at it in the editor, but that's not the way that Elm works. So I'm going to continue defining this. We'll have heart. I wish I could scroll this up a little bit more, one of the quirks of VS Code. And we have diamond and spade and club. Right? Now we have defined those 4 values. We know that our cards will only ever be hearts, diamonds, spades, or clubs. We can't suddenly toss in circle or some other value. The type system is going to enforce this. And if I create an instance here, I can just say heart, and we see it's returned that heart is of type REPL.suit. And the same thing with diamond, and so on. So how do we make a deck of cards from this? We know what our suit is. Let's define another discriminated union pretty easily. Type card. And that's going to be ace of suit. And we've got our king of suit. Queen, jack, and rank. Now, the rank is a little different. So far, we've only associated a suit with each particular value card. We're going to have a suit, but then we're also going to have an integer. Right? We're going to say it's a value 2 through 10, right? I'm not going to go through the extent of enforcing 2 through 10 on this simple example. But now we've defined 2 discriminated unions that allow us to easily represent a deck of cards. And if we wanted to actually construct a deck, it might look something like diamond, spade, club. Now, what we're about to see here is a little deviation. So functions in Elm work just like they do in F#. They're curried, which means that we can easily construct function pipelines. So here, we're going to use the exact same operator that we would in F#, a pipe forward. I'm going to take this list of my suits and pipe it to list.map. Now, we don't have comprehensions in Elm, which is one of the things I don't really like about Elm. It would be really convenient to have that, but because it's purely functional and most of the comprehension syntaxes would require some degree of side effect, we don't have comprehensions. So we'll have to do this the long way a little bit. So I'm going to define a lambda expression right here. And the lambda expression syntax is a little bit wonky in my opinion because it starts with a backslash. It's like we don't have fun. We don't just start with a variable or a parameter name. It's a backslash with a parameter. So I'm just going to do this \s, and that goes to, and I'm simply going to return a new list. I'm not going to do all of these, all of the cards, but I'm just going to do ace of S and king of S, queen of S, jack of S, and rank of S and 10. That will get me, by virtue of the map operation, a list of lists. But I want to make it just one list, so I'll take the result of that and pipe that into another module function, conveniently called concat. And now we see our list: ace of heart, king of heart, queen of heart, jack of heart, rank of heart 10, so that's our 10 of hearts. And then we can see we switch into diamonds with the same pattern over and over. It would be easy to extend this out to define the full deck of cards, and then we can do things like shuffle the deck and work with the deck. So this is a very quick way, if we were building a card game, to get a constrained deck of cards, very convenient, quickly, and so on. So the expressiveness of the language, I think, is really brought out in things like the record types and the discriminated unions. So let's look at how these pieces kind of flow together. I'm going to close down this REPL window. Are there any questions before we move on? Nope? Okay. So I'm going to close this REPL window. And since I'm in VS Code, we have the I can't remember what this feature is called, but we have this command list that we can access into. Now, I've installed the Elm extensions. So I have this one right here. And this brings in the REPL, and we didn't talk about, we're going to see in a moment, this thing called Elm Reactor. It's a very convenient way to just run your Elm applications. This connects Elm Reactor and the REPL and the other commands inside of VS Code. And to access them, I'll do my greater than, and I'll start typing Elm. And we can see the things that are built in. So we got clean build artifact. Actually, that's, install packages, make warn, reactor start, and reactor stop. So let me go and hit this reactor start. And we now see that it's started up a web server, because this is intended to run in the browser. Let's command click on this, and that's going to give me this window. This page is where it took me to. This is the home page that Elm Reactor displays by default. The sample application we're going to look at is a tic-tac-toe application. A very seemingly simple game, but there's a lot of little rules that you have to think about as you're constructing something, and it really lends itself well to things like discriminated unions and records. So let's go take a look at this application. Reactor is presenting us with a list of our file system from wherever we started it. And I'm going to navigate into demo, and I'm going to navigate into my source folder. And before I go into index, I'm going to go into scripts, and I could go to the JS file, but it's not really going to do anything. That's the output from the Elm compiler. But I want to run the Elm code directly. So I'm going to click the tic-tac-toe.elm. And it's going to be really ugly. I'm going to warn you right now. So this thing, if it will load, sure. X's turn and a bunch of ugly buttons. The reason it's ugly, and it doesn't have to be, is because there's multiple ways to run an Elm application. So this .elm file is an Elm application. We're going to go over to that file shortly. But what we see here, number of buttons. In the HTML, if we go and inspect any of these elements, crap. All right. I cannot remember my hotkey for zooming at the moment, but I've styled these with Bootstrap. So the way, as I mentioned, we have different ways of running Elm applications. We can either run them as full screen, which is what's going on here. We can run them as headless, meaning that there is no UI component, or we can have them target a particular element. This application is written to target an element on an existing page. So I'm going to back up to the index, and now we're running the Elm application, and you can see the Bootstrap styling is all applied. So we can have this within our existing applications pretty easily, as long as we use the styles that we and the CSS classes that we would normally use in our HTML that Elm is generating. We can have a consistent look and feel. So simple tic-tac-toe application. We can click through, and it's maintaining this. It looks like it's maintaining some state. It really isn't. And I'm just clicking, and now I can see, oh, X wins. But we think about the things that are required, the rules and conditions around a tic-tac-toe application. You know, we've got this 9x9 grid. We have 2 players, X and O. We have to track whether a space has a token in it, whether it's X or O, or if it's empty. We have to look to see what a win condition is. What are the win conditions? 3 in a row, right? Horizontal, vertical, diagonal. So we have to manage all of that stuff. And we can't play in a square that's already taken, and the game is over, so there's no reason to continue allowing people to click. Well, it turns out this really is a good sample application because it takes full advantage of a lot of Elm's features, like the discriminated unions and the record types. So let's jump back over to VS Code. I'm going to collapse this out of the way. We're just going to leave that running. We're actually not going to make any code changes. We're going to just leave this as it is. And let's go find first we'll look at the index HTML to see how this gets lined up and laid out in the page. This is a standard HTML5 document. I've got some inline styles for simplicity. And then I have a container element. And down here, I have a div styled panel body from Bootstrap and given an ID of tic-tac-toe. So this is the element that's going to hold the tic-tac-toe game. And there's 2 scripts at the bottom of the file. First is the tic-tac-toe script. That's the compiled Elm. Just like I would with a JavaScript file, I'm just or the TypeScript file, I'm referencing the compiled Elm file. So it's going to go to the JS. That's what the browser understands. And then the next script element shows the target where we get the tic-tac-toe element that I just pointed out. And the next line, var app gets elm.tictactoe.embed. So the Elm code, which we'll look at in a moment, the compiler generates a module. It's got an Elm namespace, essentially, and a tic-tac-toe module, and we want to embed it in that tic-tac-toe element. So we want tic-tac-toe to, we want the tic-tac-toe element to hold our application. So let's go look at what the Elm code looks like. The Elm architecture, we break out our application into three primary areas. We have our model, we have our update, and we have our view. Okay? So you see this a lot of places. And other frameworks like, I believe it was React, have been heavily inspired by this model. So it turns out that functional applications tend to really kind of follow this pattern anyway. So this is really the standard approach for constructing an Elm application. So up front, we've got some setup. We're saying we've got our module, tic-tac-toe, and this parent ... says any function that's visible here, that's defined in here, is going to be visible externally. I don't really care. Nothing else is using it. For this, it was simpler to do this. But if you look at things like import html.events, so we're going to wire up some message handling that responds to input and click events from our application. And then we define our program. App program is a function that takes an object that defines a few steps. We have an initialization step, and then you can see the view and update, which we talked about, and subscriptions. So subscriptions, I actually don't think I have wired up in this version. But what we can do ultimately is have Elm applications communicate with the outside world through subscriptions and what we call ports. So if you have other JavaScript or other Elm applications on the same page, they have ways of intercommunicating. And because it's all going to be message-based, they will push a message into the pipeline for this particular application. It will do the processing against that message and then update the model and the view accordingly. Now, it's not managing any state, really. We have our model records that and discriminated unions, which we'll see in a moment as we scroll through. But Elm is managing that. We're not managing it. We're not setting a global variable or anything anywhere. We're allowing the Elm engine and the Elm architecture to manage that for us, and it will handle things like a shadow DOM and how the elements are displayed and where certain pieces are rendered or re-rendered. It does it in a very efficient manner. So let's take a look here. So our model. We know that in a tic-tac-toe game we have two players. Well, player X and player O. Pretty straightforward. We have those two union cases. But then we need to know something about where the cells are. So we have a X position and a Y position, left, center, right, and top, middle, and bottom, respectively. So that kind of reflects back there pretty well. I'm going to reset this because we'll come back in a little bit. But the X position and the Y position don't identify the grid, or the position in the grid independently. We need the combination of those. So we have this alias called cell position, which is a tuple type. Tuples are already defined within the language. We're just going to change the definition to the name cell position for the combination of Y and X position. We have a union that represents cell state. Has somebody already played in this cell? If so, who? So that's occupied by player. Or is it empty? We have a cell. What's a cell? Well, a cell has a position and a state. Where is it and who has played on it? And just to make the code a little bit more readable, rather than having things like list of cell, what does list of cell mean in any given context? Alias it as board. So when we see in the code below, we're going to work against the board, which is really just a list of cells. Then as players are interacting with the game, we need to know whether what they did was valid or not. Some of this is enforced by the UI. We add attributes like whether or not the control is enabled or disabled based on that particular cell state. But maybe we don't have those safeguards in place. So we have a union case for invalid move. So some player made an invalid move. Or was the move valid? Yes, it was. So the player X put their token on a particular spot. And nobody won, and it wasn't a draw. If a player puts a token in a spot and they get 3 in a row, well, that's a win. And then a lot of times, I probably should have called it cat's game, but I called it a draw here. And then our overall model for the game consists of 2 pieces of data. We have our board. Now, our board, we just said, is a list of cells. And the cells had the position and their current state, right? So we've got all of the state we need in that list. And then the last move result. Now, we could take this a lot further. I just track one move at a time, but if we wanted to implement some like undo functionality, we could actually have another list here. So we have a list of move results, which I've thought about doing just for the fun of it, just so we could kind of like back and forth and see how the architecture plays with those lists. But for this, we're just keeping it simple, and we're going to track the last move result so that when we redraw the board, we know whether we should indicate that something is won, or that someone has won, or whether it was a draw. So that's the overall model for the game. Like that's really what we need to see. That's how we represent the board and the players and the current state of the game. The init piece is just a little bit of setup that we need. When we first load the game, we need to identify the horizontal positions. That's just a list of left, center, and right, and the vertical positions, top, middle, and bottom. We have lists of those, and we essentially just build up the board from those 2 lists. So we identify all of the positions, and we create a new model with all positions piped into the map, and we're going to initialize those, all of those positions, all of those cells, as empty. And we're going to say player X gets to go first, and then this command none, this is the first part we've seen where we're tying into this messaging system that Elm is built around. This is saying we're starting off, there was no command, this is the initial state. And now we get into the update portion. An update is where all of the magic for the application happens. We see this message type here. There really are only 2 actions that can ever happen in a tic-tac-toe game, right? We have a player takes a turn, or the game is reset, right? What does a player taking a turn do? Player taking a turn needs to inspect the state of that cell where they clicked. Was somebody already there? No? Okay, well, let's put a token there. Did they win by looking for 3 in a row? No? Okay, well, now we need to accept another command for the other player. And then there's reset, which simply runs that init function again and clears out, and let me back up. It's not clearing out, and it's giving us a new list, brand new list of cells that have all been initialized to empty. So move and reset. Our move consists of who did it and where did they go. This lines to check is just some little setup that identifies our rows, columns, and then the 2 diagonals. So we do that very functionally. We've got some concatenation of lists going on where we're going to map all of our vertical positions to rows, all of our horizontal positions to columns, and then our diagonals. And we're going to concatenate those into just one nice list that we can cycle through and find very quickly. We go find the actual update function. We'll back up. So I've defined these. So everything is defined above the update. The update is the piece that Elm calls. This function is what Elm calls into. And it accepts the message, which we just saw that type, which will have the command built in, and the model. So we're always going to be passing in the model. Elm, every time we click that reset button or one of those grid squares, we're going to get the model passed back in. So we're not managing that. Elm is going to keep that somewhere tucked away, and then when it needs to work on it again, it will pass that model in, but we won't change that model. We're going to create a new representation of that model, which gets passed back to Elm, which is why we're working in a purely functional language. We're not going to change that state in any way. We're going to create a new state and let Elm handle updating our UI for us. So here we're just going to do a pattern match. Just like in F#, we have pattern matching. So case message of a move or a reset. Now I just mentioned that reset, all it does is call init, right? That gives us that initial list of cells again. But move, here we go. Here's the logic I described for what happens when a person clicks the cell. If it's, I really need to rewrite this. I started off, and I'm like, I need to make this the positive case. But if it's an invalid move, then we're just going to say, yep, this is an invalid move. We're not going to change anything on the state. And we actually can't, just based on the nature of disabling those buttons, we shouldn't actually fall into that case. But for completeness, we cover it. Most of the time, though, we're going to come in here, and we're going to create a new cell. We've got to remember, it's a position and the new state. We're going to say that this cell at this position is now occupied by the player that clicked that. And there's this function, replace cell. What this does is it takes that board that was passed in through the model, and it looks across all of those cells that are in that board, and if the cell matches, that cell's position matches the one that we're passing in the new one, we just created it, we're going to use that in place of what was already in there. So we're essentially replacing it. Well, we're going into a new list. And so without going through all of the details of this piece, essentially we're just handling these messages. We click, that has an event handler wired up in JavaScript that calls into Elm. Elm finds the update, and it runs through this update function. It gets us our updated board, and then it calls the view function, which we haven't looked at yet. Now view, is a very simple function, but I have a lot of code above it. Elm exposes a module that defines, I think, every HTML element. And it exposes them as functions. So we're going to wrap our entire board within a new div. And it takes two lists. The first list are attributes. It's just an attribute for the resulting element. And then a list of all the child nodes. So I have this build board function that accepts the model. Build board, model, we're going to concatenate building a header, building a div, building a horizontal rule, and building a footer. You can see all of those in Chrome. Our header is whose turn it is. This tic-tac-toe box is part of the index HTML. We're controlling everything here. It's not going to select everything. X's turn up through the reset button is being generated by Elm. So every time we click something, it gets that message. It processes what that new state should look like. It passes that new model into the view function, and it uses a shadow DOM to make dynamic changes to our resulting HTML. But because these are all functions, we've essentially just replaced angle brackets with square braces, right? It looks like HTML, but it's functional. Like, we call the div, that's going to give us a div element back in our resulting HTML with, in this case, we're setting the class attribute to tic-tac-toe board, and then the content for that is, oh wait, there's another function call. We're going to take our vertical positions that we defined earlier, and we're going to map it to build row. We're still passing in the model. When we say build row, take our model, take our vertical position, represented as a div, and then we're going to lay out each individual button across the board. So we take those horizontal positions and we map that to a lambda expression, to a function, takes that position, and we go and get the cell from the board. What does that look like? Get cell. Where was it? Build cell. Here we go. So we're going to get the cell. This gives us a new construct. We have this let construct. So I've got just a simple function here, but it allows me to define a variable used just within the context down below. So let cell get board, filtered down to the position, and then list head. Get the first item off of that list. Then in case cell of just or nothing. So for those familiar with F#, some or none. This is our option type. We have that same concept in Elm, getting us around the whole nullability option. We see we have a very definite case. We either have a value or we have nothing. If we have nothing, well, then we'll just create a brand new cell. Otherwise, we'll use the one that we found. And ultimately, we result in this nice HTML, the beautiful default Bootstrap theme. So the Elm website has a very good overview. Oops, there's the book and the introduction to Elm. The documentation is pretty thorough. There's a few spots that I find there are some gaps in. I'm looking forward to actually trying this out on a real project pretty soon. I think just the nature of the language, the fact that it is purely functional should allow for a lot more flexibility and a lot more predictability in terms of how I construct my application, give me that safety from the underlying types, and also just because it's ML, as I start building up more F# back-end stuff, we're able to work in a very consistent language, but one that was designed for being in the web. So we still have a few minutes here. Any questions I can go back through? Yes, sir. Yes, I can certainly show where the clicks are, the event handlers are hooked up. Let's go over there right now. So this is all coming out of our view code. And if we find in build board, we have build footer, build row. So build cell. Build cell is by far the most complex function in this, and I could probably refactor it a bit. But build cell is responsible for building up each individual square. So build cell takes a model and the cell. And it's going to create a div, and it's going to be styled. And then we look at the state. So if we have an occupied cell, we're defining a button. So we're going to invoke the button function. We're going to do some styling on it. So we've got button style that is a binding defined elsewhere, along with default. And we're also setting the disabled property to true. But if we don't have anybody on that space, then we do a pattern match against the last move result. So we're going to move into the next player, because we're not going to say that just the nature of the language. We've enforced that player X can't play twice in a row, player Y can't play twice in a row. That's why this next move case identifies the next player. So it's going to control whose turn it actually is. So next move case, we're going to execute the button function as well. We're going to do some styling. Instead of using the default style, we're going to do the primary style, so that we get the nice blue color. And then we give it onClick. OnClick function takes a move. Well, what was move? Let's go back. I'll find it again. Move is our message. It takes a player and a cell position. Find that again. I lost it. There we go. So that onClick function is going to generate the HTML that wires up the click handler. So and I'm going to expand that if I can. It probably actually looks like it's putting it in script. I would zoom in when I can. All right, yeah, it looks like it's dynamically wiring it up. It's not putting it as an attribute, so it's doing it through the script, so I can't actually find it quickly. But that is exactly where it's hooking that event handler up. And so each time the board is regenerated, because we've played player X has clicked, they have a valid move, the next player is Y, it's going to go and reconnect all of those event handlers for us so that when the next click comes in, it's going to be enforced that it's player Y making the move, and then so on. It's just going to flip back and forth because we only have two players, right? But it will manage connecting and disconnecting those events for us so that when we rebuild that, we make sure that we are getting a valid next move. And then ultimately, the reset button does the same basic thing. So we can see here on build footer, we take our button function, we give it our styles and the attributes, onClick, reset. So reset was, again, if I can find it, one of our messages. So this is going into that message system. We click that. Update gets called. If we find update, update takes the message. This line here, line 147, is the signature. These are our annotations. I actually kind of prefer this model with the annotations rather than doing them inline like we would in F#. I like having it just set aside and up above rather than in the middle of the line. But we accept the message and we accept the model, and then we return the new model and a command. So we've got our message came in, and it's going to pass back. I think everywhere I'm just returning command none. That kind of ties into the subscriptions, and I'm not really using that in this version. So yeah, very easy to wire up. Yes, sir?
Question. Now you're in a happy land using Elm and the language you want. How would it look if you wanted to actually talk to a JavaScript library?
So how would it look if I wanted to talk to a JavaScript library? Now, I don't have an example of that, but there are ways for Elm to communicate with the outside world and vice versa. So I actually haven't used it yet, and it's something I have been looking into. I wish I could find it quickly. They have this notion of ports. So it's essentially places where other pieces can plug in, and it really works off of the ports accept something, and essentially it calls into update over time. And then we can also have subscriptions that do some similar mechanism. But yeah, ports are primarily, we've got that's probably right there, JavaScript interop. So this is the Elm documentation on getbooks.io. Yeah, and I love it. At some point, your Elm program is probably going to need to talk to JavaScript. So, if you wouldn't really be necessarily, like if you're using jQuery or something like Lodash, you're not going to really use that in your Elm code directly. You're going to stick in Elm as much as possible. But every once in a while, if you have other things on your page that you need to interact with, you're going to look into things like the ports and the subscriptions. Is that what you're looking for? All right. Anything else? Yes, sir.
In terms of resources, what I found that tied everything together for me best, for resources for learning this was elmtutorial.org. It brought together all the moving parts of an entire app and kind of crystallized it well for me.
What is it, Elm Tutorial?
Elm-tutorial.org, I think, is the... Yeah. But it ties it in with Webpack and all this, super sci-fi web stuff that gives you the full... that just as a recommendation. I liked it a lot.
Yeah. I don't think I've actually been to this one. Yeah, thank you. Yeah, Mark.
Does Elm have some sort of syntax like F-sharp's computation expressions or Haskell's do notation?
Does Elm have computation expressions? I don't believe so, but I'm not sure off the top of my head.
Okay.
Yeah, I would be, honestly, I'd be kind of surprised if it does, but I haven't looked.
It doesn't really because the language isn't as powerful as Haskell.
Right. Yeah, it really is focused specifically. It is more of a domain-specific UI language. Yes. Anything else? No? Then we're almost at time. Thank you very much for coming out. I'm Dave Fancher. Please fill out an eval card. The complex operation of moving it to the box. I appreciate your time, and I hope you learned something. Thank you.